All right. Well, I want to echo a sentiment that I heard from other speakers, and that this talk was a lot harder to write than I expected. And I think for me in particular, I've spent a significant fraction of my career telling people what JWST should be capable of. And now we're actually here. And so, we need to really pivot away from thinking about, just projecting forward and looking at the here and now, which is part of what I'm going to focus on, and thinking about where we want to go as a community in the next 20 years. All right. So throughout the presentations that you've seen here, JWST observations have featured prominently. In particular, we've seen quite a few talks feature the observations from the Transiting Exoplanet Early Release Science team, specifically the observations of WST-39b and the detection of carbon dioxide and sulfur dioxide in its atmosphere, which was super cool, don't get me wrong. But I also want to highlight that a big part of the early release science team's observations was that they wanted to really exercise the observatory and sort of take it for a test drive for all of our benefit. And what you see here is actually observations of WST-39b and transmission from all of the near infrared instruments on JWST. And I do want to highlight that these spectra are absolutely amazing. And we're already seeing water, carbon monoxide, potassium, of course, our friends, sulfur dioxide, etc., in these spectra within just, basically a few months of science operations with JWST. You also heard from Emily Rauscher about some of the amazing work that was being done for emission spectra and, in fact, eclipse mapping with JWST for the target WSP-18b. And again, the precisions that are being achieved right out of the box with JWST are allowing people to map planets in multiple dimensions and, of course, detect new species and see emission from these planets at wavelengths where we have never seen it before. And of course, many people are excited and interested about terrestrial worlds, in particular the TRAPPIST-1 system, and I'm not giving any spoilers in this talk here. But what we're already seeing, again, within the first few months of operations is that we're able to achieve precisions that allow us to really break down the phase space that these planets might exist in, which is a really important step as we move forward to guide what we should be looking for in the atmospheres of terrestrial planets around M dwarfs in particular. Now, these spectra and photometry are amazing, and it's great to compare them to models. That helps us to understand sort of what we're seeing. But I want to take a step back and remind you that every transiting exoplanet observation with JWST is its own little mini deep field. All right. It's a long duration stare at an exoplanet hosting system, usually hours in length, sometimes more. And when the data comes down from JWST, it looks simply spectacular. There is clearly a planet passing in front of a star here, and these are from the early release observations, the first observations that we got to see from JWST, and this is for the hot Jupiter WSP-96b. Now, the talk I was asked to give was to look forward to the next 20 years of JWST observations. And it's kind of hard to do that right now based on where we are. We're in a precarious position. Cycle 1 operations has finished. Well, I'm still getting cycle 1 observations, just got one this week. And we, of course, have selected cycle 2 observations that have just begun, but we have not really seen the full breadth of what's coming from our cycle 1 and cycle 2 observations. We are still just seeing sort of the forefront of what's to come. And so instead of me trying to forward project from a single data point and probably getting the slope very, very wrong, what I'm going to do is actually backward project and give you an idea of where we've been. I'll come back to the future, don't worry. In many ways. We'll see if anybody else catches that reference later. All right. So you don't really know where you're going until you know where you've been. And I want to say that part of the reason why JWST for transiting exoplanets worked so well right out of the box, right out of the gate, and gave us those amazing initial observations was that we've had now 2 decades worth of observational science and also theoretical development to build on. I do want to remind folks that Hubble launched in 1990. I'm guessing that probably is before many of you were born, but that was before we even knew about any exoplanets, let alone transiting exoplanets. First transiting exoplanet was discovered in 2000, and Spitzer was launched in 2003. And I'm going to focus mostly on Hubble and Spitzer here as sort of precursors to what we're achieving with JWST. But I also want to highlight that there was a huge growth in the number of targets that we consider through missions like Kepler and TESS that have been critical to sort of the science that we're now seeing with JWST. But Hubble and Spitzer were not designed with exoplanets in mind at all. They either didn't exist yet or had been barely formulated. And so there were a lot of challenges there. I think the other thing to keep in mind from a theoretical perspective is that, with the detection of 51 PEG B, that sort of opened up a whole new floodgate on atmospheric scenarios that we should be modeling and considering. For a long time, we were thinking about solar system analogs and what they might look like around other stars, but suddenly you get the fun job of taking your Jupiter and parking it right next to your star and seeing what happens. I think it's fun. And so that opened up a whole nother sort of area of research. And in my mind, observations and theory have sort of gone in tandem. Sometimes theory leads observation, sometimes observations lead theory. And in fact, the first clear detection of an exoplanet atmosphere was a case where theory led observation. So there was a detection of the determination that HD 209458b, in fact, transited its host star as seen from Earth. And then immediately, several groups were like, hey, you should be able to see sodium in its atmosphere in transmission. Someone was able to convince Hubble that they should go look for that. And they looked at a transit of HD 209458b using Hubble's STIS instrument in 2001, and in fact saw that there was more absorption as the planet transited the host star as compared to out of transit. And so that's our official detection of an exoplanet atmosphere. Now, Spitzer launched in 2003, and early on, people sort of thought, hey, we might be able to actually use this facility to measure light or lack thereof from these transiting exoplanets that they knew of, these hot Jupiters mostly. And so there were a lot of early observations where groups were using various modes on Spitzer to measure the thermal emission from hot Jupiter atmospheres. And that was really great. We were actually, I want to remind you again, when we're looking at a transiting exoplanet system, we are looking at the combined light of the planet and the star. And so we can use those eclipses to understand how much of that light is from our planet. We're measuring actual photons from planets that are, tens to hundreds to thousands of light years away. I also want to take a moment and remind people that we actually had spectra of transiting exoplanets from Spitzer. Isn't this beautiful? No? Okay. I mean, I love it, but it's kind of like only a mother could love. I think why I want to highlight, there's only a handful of these. And these are one of these things where I'm like, when I get enough time, I'd like to go back and revisit that, but I never have enough time. But even looking at that, you can start to see how powerful infrared spectroscopy can be in the characterization of exoplanet atmospheres. And maybe they weren't thinking about JWST in the future, but certainly now that we have JWST spectra in hand, we should go back and look at what Spitzer had told us from these early observations. Now, the spectroscopy on Spitzer relied on the observatory having cryogen. And so once it ran out of cryogen, it was predominantly photometry that we relied on. But photometry has taught us a lot about exoplanet atmospheres. And I do want to emphasize that even in the era of JWST, with all its fancy fandangled spectroscopic modes, don't overlook the potential of photometric measurements to give you something that's perhaps more precise, to provide better guidance to follow up spectroscopy, or even to just answer the science question that you have at hand. And one of the first sort of inclinations that these worlds were maybe a lot more complex than we had been previously assuming was our first foray into looking into the atmosphere of a sub-Jovian world. This is GJ 436b, which we have JWST observations of in hand. And again, I'm not going to talk about those. And what we saw here was that there was clear evidence for disequilibrium chemistry in this planet's atmosphere. Now, over time, everyone got much, much better with using Hubble and Spitzer, and also new modes came online. All right. I will say probably that Hubble's spatial scanning with Wide Field Camera 3 really sort of blew open the door with the ability to use that observatory to study exoplanet atmospheres. It allowed us to look at brighter targets and to reach higher precisions, which gave way to these phase curve observations of WST 43b, where you're able to actually map this emission spectrum and see the water emission sort of come and go around the planet and get an idea of its thermal profile as a function of longitude. And it got people really starting to think like, hey, we can measure gradients in these planetary atmospheres. And I'll go back to Emily Rauscher's talk and think about, would we be able to see, say, clouds on one terminator versus another terminator? And what would that tell us about the underlying atmospheric circulation and the chemistry at work in these planetary atmospheres? And from the theory side, as the data got better, people started developing more and more complex models. We saw a huge growth in photochemistry models, and Julie Moses gave a great talk on Monday that everyone should watch. And also general circulation models that started to consider, not just sort of equilibrium chemistry, but also cloud formation and disequilibrium chemistry in those models as well. I will give a shout out to the development of atmospheric retrievals, which happened around the same time that spatial scanning came online. And I think that's not a coincidence. And that did really transform our view of exoplanet atmospheres. We had this really great tool to try to constrain what we actually knew about the planetary atmosphere. But what I will say, and people may think I'm wrong, maybe Mike Klein can debate me about it later, is that for a while we had what I'd like to call retrieval fever. Suddenly we were just using retrievals on everything. It may not have been the appropriate hammer to smack the nail with, to the point where papers or proposals without a retrieval in them were deemed somehow lesser. I think we've come out of that phase. I mean, retrievals are super cool, and started to realize that you need a broad range of tools to interrogate exoplanet transmission, emission, and phase curve observations in order to really get a good handle on what's going on. And I think Mark Marley in his talk said that perhaps more eloquently than I did. So as time went on, eventually we started to collect enough Pokemon, going back to Laura Mayorga's talk, that we were able to build a comparative sample and start to think about, okay, how are things like temperature and gravity affecting the processes that we're seeing here? Is it a continuum, or are we sort of seeing different stair-step approaches to things like cloud formation and disequilibrium chemistry? And eventually we made our foray into probing the atmospheres of habitable zone worlds. K218b is not terrestrial, but it does sit in the habitable zone of its system. And we were able to measure water in that system quite significantly using a combination of Hubble and Spitzer observations. And of course, all of the TRAPPIST-1 system planets got a first look with Hubble in order to guide future JWST observations. And so at the end of about 20 years, just shy of 20 years, we had accomplished basically what JWST has done in the first 6 months. So you may be asking yourself, what's the point, Nikole? My point is that with the last 20 years, we did not have a rule book. We had no idea what we were doing. And I think most people who are of that era will agree with me. But we were creative and we tried new things. In the end, it worked out. And so I think that's one of the biggest lessons learned, is that we started out with some of the low-hanging fruit. We hit the easy button for a little bit, and then we started to challenge ourselves. And that is what pushed us to where we are today with JWST. I do want to give a reminder, though, that we did have to deal with some gnarly systematics. Some of you who may only ever work on JWST data need to be reminded that this is what the data from Spitzer and Hubble looked like, okay? Even with systematics models where you can barely, there's an eclipse somewhere in there. I'm not going to use the pointer, but you can see it here after we clean it up. There it is. All right. Even with systematics where you couldn't even see a transit or eclipse, same thing here with, of course, the breathing modes and Hubble, we were able to push down to precisions on the order of 20 to 30 parts per million. Okay. And so if you can do that out of this, anything is possible, is what I want to say with JWST. And so in the era of Hubble and Spitzer, we looked at probably more than 100 transiting exoplanet systems and performed atmospheric characterization observations of various sorts, transits, eclipses, etc. In the era of JWST, given its lifespan, I see potential for more than 500 transiting exoplanet observations that aim to characterize those planets' atmospheres. And I always get asked the question, where does that number come from? I didn't just pull it out of thin air. I am actually using what we've learned from cycle 1 and cycle 2. Now, before cycle 1 and cycle 2 selections were made, I was always hedging my bets. I would always get up and be like, maybe more than 300. But I think I can confidently say, given what we've seen in the first 2 cycles, and given that JWST's expected lifespan will be up to 20 years, that we have plenty of opportunities to characterize hundreds of exoplanets. In cycle 1 and cycle 2, we have about 120 individual targets, more than 300 observations, totaling around 2,800 hours. This is 20% of geo time is transiting exoplanet science. Okay. If we look at cycle 1 targets, and this is a plot that you saw earlier this week from Hannah Wakeford in sort of mass radius space, we can see that already we're getting a nice spread in terms of the planet sizes that we're probing, even through our cycle 1 programs. Add in the cycle 2 programs, and that trend continues. So part of what I'm forward projecting is that we as a community don't seem to glom on to one end or the other of the mass radius space that we want to consider. And so we are actually building a very nice comparative sample of exoplanet observations, whether or not that was in our intention. The other great thing is that these aren't all transits or eclipses or, God forbid, phase curves. Although phase curves are awesome, don't get me wrong. They are a good mix of both transmission and emission that's going to be really, really powerful as we move forward. All right, so here we are at the end of cycle 1 and cycle 2, or we're end of cycle 1, entering cycle 2. And you're going to ask me again, where are we going, Nikole? Oh, sorry. And I'm going to tell you, wherever you want to go. I think it's important to remember that JWST is a general use facility. Okay. It's what it does is primarily driven by the proposals that are submitted to use it. And while I have ideas of where we should go, I think it's important that you realize that you have a say in what we do in the future. Okay. Now, one of the things that I do worry about, though, is that we're going to grow complacent. Honestly, JWST data is so nice and actually easy to use, having spent my sabbatical relearning how to analyze data, that we might just keep hitting the easy button over and over and over again. And if you take nothing else from this talk, is that when we had Hubble and Spitzer observations, we were really challenging ourselves to use the instruments in not the ways they were intended, to think up new types of observations, to develop new theories that might challenge those observations or guide future ones. And so we need to keep that sort of, for lack of a better term, Wild West spirit alive as we go into JWST. We need to keep pushing this observatory to its limits for the next 20 years. And that is my challenge to you. And those are the types of good choices that I hope people in this audience are going to make. And a reminder that the JWST Cycle 3 deadline is coming very soon. Actually, I'm terrified at this point. I don't know how we're going to get everything done before October 25th. And I'll encourage everyone in this room to either lead or participate in submitting a JWST Cycle 3 proposal. And if you need a quick roadmap for how the heck you would even approach something like that, I've put one together to you. I won't linger on it too long, but I do want to highlight a few things. The first is that you need to always start with a science question. I think often we start with the mode or a planet and sort of work backwards to a science question. And I don't think those are as compelling of proposals. But once you got a good science question in hand, you can start to think about, okay, what planets, what observing modes might be most useful to tackle that. I also want to highlight that we have specially designed tools that will help aid you in sort of understanding the signal to noise ratio you'd be able to achieve and making sure that meets your science goal. And I want to give a big shout out to Pandexo, which was written by one of our speakers yesterday, Natasha Batalha, specifically for JWST. The other big thing is that I want you to make sure that you have a team put together that can tackle both the proposals and the observations that come after. And I want to ask you to consider the diversity of that team along many axes, because having people with different experiences, different ideas coming together often results in some of the most robust and interesting proposals. And then finally, you'll have to, of course, write, polish, and submit your proposal. And that means interfacing with our dear friend APT, which you can ask me about later if you like. This is just a reminder of the modes that are available on JWST for transiting exoplanet observations. Again, this is mostly here for reference. I'm not going to read them all to you. Key thing is it's actually an overwhelming number of options. I'm used to having like 2 things to worry about. There are a lot of ways that you can observe transiting exoplanets with JWST, and that includes spectroscopic modes on all 4 of its instruments, and then photometric modes on MIRI and NIRCam. I also want to highlight that we're getting a new mode in Cycle 3, and I'm excited. Anybody else excited? Okay, Kevin's excited. Great. Taylor's excited. That's all that matters. All right. So some of the modes on JWST were actually sort of back designed. And in fact, this is one of them where we're using a set of grisms that are actually used to align the mirrors on the telescope, which is great because you want to keep the telescope in focus, although I would love to defocus the telescope. And we're going to use it for science. And so with NIRCam, you can now get 1 to 2 micron spectroscopy combined with the longer wavelength channels. This produces 10 spectra of about R300, which is interesting. But the key thing for me is it can look at targets as bright as about K1. So this is really opening up sort of a bright target space. And you may look at this and be like, oh, this is new and scary and untested. Well, I'm excited about that. But if it's scary to you, I'm gonna say this for you. There are no insurmountable challenges to transiting exoplanet observations with JWST. You can quote me. All right. Nikole told me I could do it. That's fine. You can put that in your proposal. And I'm saying this with confidence because, just experientially, we've overcome a lot of challenges already. And I think one of the key things we learned from Hubble and Spitzer is that there are a lot of systematics we're going to have to deal with. Some of them we already knew were coming. Our lovely friends, the ramps. We've taken techniques developed for Hubble and Spitzer and applied them quite successfully, and we'll probably refine that process over time. There are systematics that are specific to JWST, these mirror tilt events you heard about earlier, and then of course, 1/f and background noise, which is very, very different than what we've dealt with before. But we've already developed strategies to get around these and push closer and closer to our precision limits. I do want to highlight that we will continue to face challenges, both in terms of noise sources, such as from the stars, the fact that we're going to have to start actually dealing with the 3D structure of the planet, and has been highlighted in many talks, we're often missing some of the foundational data that we need to interpret these observations from laboratory work. There's probably stuff that I haven't even thought of that we're going to find. Okay. As we always do, as we push to smaller and smaller precisions, we're going to find new instrument systematics, new theories, new data that we need. But the key thing is that if we keep a collective goal in mind of what we want to achieve, and if that collective goal is that we want to push JWST to its limits for the next 20 years to ensure that we get everything we want done for transiting exoplanet atmospheric characterization, we're going to get there together. Okay. And this is not to say that we shouldn't have, individual contributions or that individual ideas, et cetera, are important. It's just that we are a big enough community now that if we don't focus on moving together towards a common goal, we will often sort of trip each other in the process. Okay. So think about that goal, keep it in mind, and we're going to move forward. I also want to highlight that workshops like these are super important, and I think Dawn would agree. And I'd like to see a lot more data challenges, collaboration meetings, et cetera, where we have this opportunity to build new connections and move together as a community in characterizing transiting exoplanets. And just briefly here at the end, I also want to remind everyone that JWST isn't the only space-based facility that will be doing atmospheric characterization in the coming decade, and that we really do need to think about the synergies with other missions. I also want to highlight that Hubble's not dead yet, and that it's still providing critical access, especially to UV and optical wavelengths. And there's several people who've given talks this week that are part of the Strategic Exoplanet Initiative with HST and JWST working group, and they wanted me to point you to this website, so please click it. And also that on Monday, there is a town hall that is reserved for early career researchers and that you should join. Last 2 slides. Finally, I would also remind you that there are plenty of opportunities for atmospheric characterization from the ground, and we should think about synergies between JWST and ground-based observations. And finally, I'm going to leave you with this, okay? My first exoplanet meeting, there were 50 of us. This meeting, there are now more than 1,000. And so part of what we're going to see for transiting exoplanets in particular is that we become a much, much larger field, and that's going to change the landscape. But I hope everyone will move forward towards really bright future and pushing the limits of JWST for transiting exoplanet science. That's the end, sorry.
Have time for a couple of questions. Here's to the audience. Let me start off by just asking one myself.
Okay. Okay.
Yeah, we're going to observe a lot of planets in probably many, many different ways. One concern I have is that recognizing how important it is to cover planets with many different wavelengths and many different modes, are we going to have really sort of a hopscotchy way of covering these planets, or are we going to be able to fill in enough so that we get the full redundancy and the benefits of that?
So your worry is that lots of individual geo programs won't make the spectra that we need. Again, I'm not concerned about that. I think we as a community, especially as we've seen with HST and Spitzer, have learned how to fill in the gaps. And I also just want to motivate also, if you need the full wavelength coverage for your science case, ask for it. Don't be like, oh no, it's a medium-sized proposal. And I think that's one of the things that we have to sort of get over, is that everyone wants to do little one-offs of things, and you're right, they might not get stitched together. But if you have a really compelling science case that requires observations that go all the way from 0.6 out to however far we can go, then you should ask for the time to do that. And I think we will start to see large surveys, and we already do have large surveys that do this in a coherent way. So I'm not concerned. I don't use the word concerned in general.
Earlier in the week, somebody mentioned that the first round of James Webb proposals seemed to lean towards transiting planets or transmission science, and then the second round leaned towards eclipse spectra or emission science. And I might be misremembering that a little bit.
Mhm.
Do you think that was deliberate from the TAC or from the proposers, or that just the way it fell, or totally, look at that?
Yeah, I think there's a lot of random walk that happens with any proposal process. I mean, there are people in the audience who deal with these things. There will be variations from who's on from TAC to TAC. There'll be variations from proposal to proposal. So I think there is a certain amount of randomness, but over time we may see how things evolve. If certain techniques prove to be a lot better at accessing certain science questions, and the community will move towards that. And we've seen that historically. Sample of 2, basically. This is my problem, is I have 1 point and I'm like, which way do you want to go? So
We have one online.
Yes. So this question is asking on your third slide, you show simulated spectrum of bare rocky surface with no atmosphere, the ultramafic rock. The question is, why do you think atmosphereless body has to be ultramafic rock?
all right, so that is in response to the TRAPPIST-1c observations, and it was covered in Laura Kreidberg's talk from, was that Wednesday? But basically, again, this is a single point photometry, and what we're doing with these terrestrial worlds, both through transmission spectroscopy, but also these really awesome photometric observations, is we're trying to narrow down the phase space of what we think might be possible for their atmospheres. And so what they were showing in that plot was a range of different atmospheres, but also just what you would see if there was no atmosphere and you were actually getting signal from, say, an ultramafic surface. Do those 4 lines actually encompass all the possibilities that exist out there? No, but this is just informative so you'd understand what it would look like as a bare rock versus various other atmospheric scenarios.
Okay, do we have one more question in the room? In which case, one more online.
So this is asking, will the JWST data for the next cycle will be publicly available immediately?
So the availability of data varies from program to program. And if you go and look at the selected programs list on STSCI, you can actually look at what's called the exclusive access period for programs, and it'll tell you. Large programs are always 0 exclusive access, which means those programs' data are available immediately. All of the early release science observations were also like that. And sometimes observers actually just say, I would like my data to be available immediately to the community for a variety of reasons. So you just have to go through and look for cycle by cycle. But after 12 months, all the data will be available to anyone who wants to look at it.